thank you all for having us here today to give a talk. I'm really excited to be here and excited to have helped with the Friends of Taunton Bay's proposal to Maine Sea Grant and just to be studying Frenchman Bay because it's a beautiful place to study. So I feel very fortunate to go out on the water once a week and get to collect data around this beautiful area. So today I'm going to talk about some of the monitoring and modeling that we're doing in Frenchman Bay. And when I say we, it's the WHOOPIES group is what we call it, the Watershed Process and Estuary Sustainability Research Group. And we're modeling and monitoring in order to understand material transport in the bay. And when I say material, it's like anything in the water. Any stuff that you can have in the water. So that can be, pollution or harmful algal blooms or microplastics or, salt. It can be sediment. So we just want to understand how that moves around in Frenchman Bay and the surrounding estuaries. Okay. So why are we monitoring and modeling in Frenchman Bay? We want to help, as Alice said, we do stakeholder-driven research. So we want to help develop decision support tools for our stakeholder partners, which includes DMR, along with some shellfish harvesting companies around the bay. So we work with Acadia Aqua Farms, the DeConings in Jordan River, and also Waukeg Neck, and I probably said that wrong. I feel like I always say that wrong. But Graham Plattner's oyster farm that's right by Bean Island, just at the lower reaches of what we call Sullivan Estuary. And we want to develop these decision support tools that are related to primarily coastal pollution and harmful algal bloom transport. Our objectives are, like I mentioned, to better understand circulation in the bay and surrounding estuaries in order to understand material transport, what we call residence times, which I'll explain in just the following slide, drivers of harmful algal blooms, and eventually, as part of a big USGS-funded project that we have, we want to develop a forecasting tool for our stakeholders to be able to use that's available online for anyone in the community or other partners to look at and be able to anticipate where, again, material is moving in the bay in a 2-day forecast. And I'll talk a little bit more about that as well. And just to give you some idea of our team, so we've deployed instruments. This is right behind Bean Island, a sensor that measures the current velocity throughout the water column called an acoustic Doppler current profiler. This is an undergraduate research assistant, Nick Tyner, who is filtering for harmful algal bloom cells and also microplastics. We have Dr. Sean Smith and Taylor Bailey, a PhD student of mine, who is, they're deploying what we call a shellfish box that has either oysters or mussels in it, and we take those meats once a week, grind them up in a blender, and then send them off to be tested for domoic acid, which is a harmful algal bloom toxin. And then this is also Taylor, using a really cool piece of equipment called a micro conductivity temperature and depth sensor, and that measures mixing in the water as well as salinity and temperature and turbidity at 512 hertz, so 512 times per second. So we're really trying to get some really good data in the estuary. So, and we need good data, and we need a lot of data to be able to accurately model, right? So we do a lot of our monitoring in order to have good models. Ooh. Okay, and then so now what are we monitoring in Frenchman Bay? So this is, I'm sorry, very small and you can't see the text very well, but this is Frenchman Bay. This is sort of our study domain, and all of these different symbols that I have are different places where we collect data. So you can just see if there's stars or purple dots, everything means that we collect some kind of data there. And we started collecting measurements in 2017, so we've been around for a little while, starting in the Jordan River, and we've sort of expanded since. We measure current velocities. So this is the acoustic Doppler current profiler. This is an example of that instrument. And we've measured those velocities in Jordan River behind Bean Island, like that picture in the previous slide, and in Frenchman Bay. This in June of 2022, we did a tidal cycle survey along this purple line. So we were out for 12 and a half hours collecting data to understand a full cycle of the tide. In June 2022, this is the survey, the tidal cycle survey. We had one boat. This is our ADCP that has its own little special boat off to the side that we just tow back and forth for 12 and a half hours. And then here we have Dr. Sean Smith. You can't really see his face very well from where you guys are sitting, but he looks sort of tired and looking out in the distance because it was a really long day. And I was on the other boat collecting other data at the same time. We also collect data on salinity, temperature, and water level. We have these little level loggers placed at least 5 different locations around the bay to measure tidal range, how that changes, and then salinity and temperature profiles with this little thing called a castaway. So every time we stop, we put it down so it goes all the way to the bottom, and then we bring it back up. So we get a profile of how salinity and temperature changes from the surface to the bottom. We have live stream flow measurements. So in Kilkenny Stream and also in Egypt Stream, Dr. Sean Smith, he's a fluvial geomorphologist. So he put stream gauges out in both of those. And on our WUPIs, our Watershed Process website, you can go and look at the data. It reports it in real time. So if you ever wanted to see what the discharge of those streams are, we have that available, as well as temperature data as well. We're also sampling for water quality parameters. So if you can see these yellow stars that we have, we're measuring nitrogen, phosphorus, and this year we got another grant from the Maine Outdoor Heritage Fund to add nitrate plus nitrite, silicate, and ammonium to those measurements. And that is, the main goal is, also a pH and dissolved oxygen. And we want to link those water quality parameters to the onset of harmful algal blooms in the bay. And then finally, we are also collecting data on harmful algal blooms by doing the filtering that our undergraduate student was doing and actually looking under a microscope and counting the cells of the harmful algae. And then we are doing the shellfish testing where we grind them up and send them away. And we're doing some exploratory work on microplastics. And I'm working with an environmental engineer, Dr. Oner Akul, who's really phenomenal. And he works on microplastics and also PFAS. He's one of the experts on PFAS. With him and his team, we have a joint study where we're trying to do the first analyzation of microplastics on this side of the bay. Yeah, so results to come. So we use our numerical model to extrapolate these data. So with data, there's only a certain amount of times and days and places that you can be at once, right? But with the numerical model, you can take the data and you can look at what's going on in the whole bay, as long as you validate it well with the data that you collect. So this is our numerical model domain. And here the red colors and the blue colors indicate the depth. So where it's blue, that means it's pretty shallow, and where it's red, it's very deep. We have all of these gray dots or green dots are places where we force the model with river flow, so realistic river coming in. The green are the ones where Sean has his real-time sensor, so we have actual river flow data. The other ones are USGS stream stats. It's a model, it's a monthly average, it's as good as we've got. But we use that to force freshwater input into the model. And at these two boundaries around Mount Desert Island, we force the tide. So with both the water level and the currents. The model it's a science words, finite element model. But the bathymetry was from NOAA. and we don't really have very good data for the bathymetry of the streams. And the bathymetry means the bottom profile. So what the cross section of the river looks like. So that data would be helpful for us, but right now it's unavailable. The model resolution is between 1 meter. So that means the distance between places where we calculate velocities and salinity and temperature is 1 meter upstream, and it goes up to 1 kilometer at the outer boundary. And we have to make it big at the outer boundary because we have these big computers that are trying to calculate water levels and salinity and velocity, but it takes a lot of time. So one run of like a week could take up to 15 days of computer time to simulate. So yeah, it takes a lot. Okay, I said the river discharge, explain that. The tide is, right, so we force the tide, water levels, and currents at that boundary. And we can include wind, which we are starting to do now, but the results that I'm going to show you today do not include wind. And then we can simulate currents. So this is showing the velocity magnitude around Frenchman Bay and Blue Hill Bay. And where it's red, that's where it's fast. And where it's blue, it's not as fast, right? So you can tell that in the narrows here, you really have some strong velocities, right? Same thing in Jordan River and what we call Skillings estuary, you have some strong velocities. In Frenchman Bay, it's not as strong, but that makes sense because you don't have the tide that's being, like, for lack of a better word, like mushed or squeezed into a small area, accelerating the currents. And then our first step is to validate the model. And I feel like there's a lot of people looking at models these days for, like stuff with the aquaculture farms and things like that. So whenever you're looking at models, and what validation means is that you compare apples to apples what the model's outputting to data that you've collected. And you see if they match up perfectly. So again, it's kind of hard to see, but this is salinity. This blue line is salinity. The black dot, the blue line is salinity from the model. The black dots are our observations, right? And we try to compare those. Here, the blue line is model, and the black dots that are right over that is data, right? So we want to make sure that those match up perfectly. If you're going to report model results, you want to make sure that it's reporting something real, because if you don't validate it against good data, then you don't know if you can trust it, right? So that's our first step. And then we've done this validation with velocities in Jordan River, in Sullivan, and at Bar Harbor. So those are our locations right now. But a model is only as good as the data you put into it. And one of my PhD students had this quote, and I really liked it. All models are wrong, some are useful, right? What's real is the data, right? That's what's really telling you what's going on. We use models as a tool to try and help understand, but they're not 100% accurate. They can't be, because we can't reproduce all of the different variables that are going on in the bay. So now I'll talk to you about my model results. So what we want to do is determine something called, we want to use a tool in our model called particle tracking to find out residence time. Okay, so residence time is the amount of time that it takes for a material or something in the water to exit the estuary, right? So this is our domain, and here's Mount Desert Island, so here's Taunton Bay up here. And all of these different estuaries, we drew lines, and this was actually one of Sean Smith's PhD students, B. Van Dam, went to, or we had a meeting with DMR. Were you there? Yeah, you were there. And we had this, she had this big map of all of the Maine coast. And it was like, what's an estuary to you guys? Where would you draw the line for where the estuary ends? Because that's hard, And so we got DMR to draw these lines for us. And that's how we color-coded all of the different parts of this bay. Okay. And then what we did is this is a zoom in of this black area, is we put particles near the surface, in the middle of the water column, and near bottom. So if we zoom in, they're evenly spaced. They kind of look like this in a grid vertically. And we gave each one of them a tag. So we can tell where each particle starts, where it goes, and how long it takes to get there. And so what that does is if we have something like pollution, right? We want to know how long it takes to cross that line, to get out of the estuary. And that's residence time. And that's what we're trying to calculate. Right, and so our particles are proxies for the stuff in the water. Pollution, microplastics, harmful algal blooms, whatever we're trying to study. Okay. So with the particle tracking, here we can see everything's color-coded. We can calculate residence time. We can also understand how different water bodies are connected. And we can change forcing. So how does the residence time change if you start at spring tide versus neap tide? So you have strong tidal forcing versus weak. Or if the river discharge is high versus low, right? So we did a bunch of different simulations, and I don't know if you guys can see okay, but the particles are moving, and mixing around, right? So we ran these simulations for as long as it took for all of the particles to leave each of those lines that we saw before. So all of these estuaries have a similar tidal range and mixing of fresh and salt water, but their watershed size varies and the shape of the estuaries vary. So from that, we determined what residence time is. What are the most important factors influencing residence time? Is it tide? Is it river discharge? Is it estuary shape? And we calculated residence time. The residence time. And this is just a zoom in of our estuary of interest for the night. So you guys can see, and I can also give you, or you have this presentation to share, because it's really neat. Like, you can see that the particles really speed up in the constriction, and some of them, like, it takes a long time for them to leave the upper areas. It's quite interesting. And then we come up with these maps. So this is a heat map that tells us residence time. So you can see the colors represent days. So that's the number of days it takes for those particles to leave these lines. Where the orange color would be longer residence time, the green color is shorter residence time, right? And we published a paper focusing on Jordan River, Sullivan, and the Union River, if you guys are interested. And some of the results from looking at those three estuaries in particular was looking at how residence times changes with forcing conditions. So this one's Union River. I hope the shape makes it sort of apparent. Ellsworth is up here. And then this case here is where we have weak tidal forcing and weak river discharge. So that would be almost a worst case scenario. It would take a long time for things to flush out if tidal currents are weak and river discharge is weak. And we found that the average residence time in the estuary is 9.12 days. Changing our conditions to have strong river discharge or strong tides, or not including salt, because we wanted to know how important salinity was, which it's really important to include. But we found that with our worst case scenario of 9.12 days, when river discharge is strong, we have a high river discharge event, it decreases to 5 days. So in the Union, river discharge controls residence time. So one of our findings. In the Jordan River, you can see it's very green. So that means that the residence time is really low, just in general. And with our worst case scenario, it was 1.5 days for the particles to leave on average. And then whenever we had a really strong tide, it went down to 0.7 days. So in the Jordan River, tides control residence time. And then finally, in Sullivan, we found that for our worst case scenario, the average was 5.6 days, but you can see in the upper bay, it's more orange than the lower bay. And so we feel like there is like a hydraulic control with the residence time. So stuff that's up here in this bay, because of this constriction, sometimes it just gets trapped up there, right? But we did find that whenever the tides are strong, so it's spring tide versus neap, the residence time decreases to 4.7 days. So we think that tides in estuary shape control the residence time in Sullivan Estuary. And we go into detail in this in our manuscript that we have. If anybody's interested, I'd be happy to send it to you. I'll give you my email. And we also determine how the estuaries around Frenchman Bay are connected, or interconnected, we like to say. So for this one, we're investigating the connectivity of Sullivan Estuary to Frenchman Bay and to Skillings. So the black line that you see here is going to be the particles, the percent of particles, which is on the y-axis, and then days is on the x-axis. So we go up to 30 days, so we simulate 1 month. And the black line is going to show what particles are in Sullivan. The yellow line is the particles that were in Sullivan but went to Frenchman Bay. And then the red is they were in Sullivan and they're going into Skillings. And so I'm going to run that. So we can see that the percent of particles in Sullivan decreases. We have that with time, the yellow line increases. So most of the particles go into Frenchman Bay, but then they're also going into Skillings as well. So we can determine how connected each of these systems are. And then finally, we sort of get a peak with Skillings, and then everything starts to decrease, and all the particles end up going into Frenchman Bay at some point, which makes sense. But we can also do this in the other direction. This was what's going from Sullivan out to other places, but we could determine what's in Frenchman Bay going in as well. So those are sort of the highlights, the main findings of our research so far. And we're continually working on other stuff. So we have a couple of next steps that I would like to talk to you guys about. Okay, so one of our next steps is helping understand how long pollution events remain in estuaries for 1, 2, and 3 inch rainfall events. So for 1, 2, 3, 4, 5 different rivers, we are releasing particles throughout a 2 inch rainfall event in 24 hours. And then we want to determine how long those particles stay in a specific estuary. And hopefully we're going to be talking a lot with Hannah about this so that we can hopefully help DMR. And we want to also link the particle transport and the residence time of the freshwater discharges to salinity as well, which that's what you see as the background color here. Where it's blue, it's more fresh. Where it's yellow, it's more salty. Next is the model forecast. So we're expanding our domain to include all of Mount Desert Island. And we're going to have this running and put online on our website. And we're going to have specific points that have particles, and we're going to do the forecast of 2 days. So that should be done by the end of 2023. We should have that available online. So it's something that we're working on, but it's kind of hard because we're working with the computer scientists and also the Maine state climatologists to get forcing forecasts for winds and precipitation and river discharge and stuff. We're analyzing those data that we collected in June 2022 to verify the existence of a gyre around Frenchman Bay. So we think that there's an accumulation point. There's some gyre-like behavior in Frenchman Bay due to the island chains here. And preliminarily, we see it. It's there. We just haven't published the data yet. So we're working on post-processing of it, which is pretty cool. And then we're also trying to link hydrodynamics and water quality parameters to harmful algal blooms. So that's just in the works. We have this really extensive field campaign last summer, this summer, and next summer, where we're out once a week for 16 weeks collecting all the data that I was talking about before. Yeah.
What is a gyre?
A gyre. Okay, so that is like a horizontal current circulation pattern. That's like a circular circulation pattern. And so with these gyres, you can see almost like a whirlpool, but not as strong. Stuff accumulates in the middle of them, which is why we're interested for harmful algal blooms and for microplastics, because we think that it could be a point where they would be elevated because of that. Cool. And then I just wanted to say thank you to everyone. That's us stuck in the mud in Jordan River, my students. And we have a lot of collaborators and just so many people to thank for all of this work. And thank you all for listening. And this is our website, and that's my email too. So if you have any follow-up questions later, or want papers or anything, have any ideas for our group, let me know. So we're studying a specific kind of harmful algal bloom, Pseudonycha, and that one is just around, it was just found on the coast of Maine in 2016, was the first time. And it creates amnesic shellfish poisoning if a human eats it. And that can cause neurological symptoms, short-term memory loss, and can be fatal. And that one is new. And so it was like, why all of a sudden is it here? And so that's what we're investigating. But other ones like paralytic shellfish poisoning, and I forget the cell for that. Alexandrium, yes. Yeah. That one's been around for a long time.
1972 was the first time we recorded it here. And then we have DSP, which is diarrheic shellfish poisoning. And that has been around for a long time as well. We're just seeing it in larger numbers lately than we have before.
Yeah. Mm-hmm. Yeah, and so I think that there's closures quite frequently, more for PSP, I feel like.
Every year for both.
Every year for both, okay.
Yeah.
And I really wish Sean was here because he's the river guy. But his plan is by the end of the summer, he's going to put one of his stream gauges just, I think just upstream of the dam. No, I think it's downstream. Just downstream of the dam, so that we can get accurate river discharge for the model. Because right now, I think that does cause a problem, and with stream stats, it doesn't register that. And it's one of the largest freshwater sources that we have. So we need better freshwater data because it's so important. Yeah.
I'm Hannah Horecka. I work for the Department of Marine Resources. I am a water quality scientist with our Bureau of Public Health. So our job is to make sure the shellfish that's harvested in this area is safe for people to eat. As Alice said, my area extends from Stockton Springs to Scudic Point, and so I'm the one that makes a lot of the decisions of whether people can harvest in bays. So I'm not always well liked, but I try to do a good job. Let's see. So first of all, why are we concerned about shellfish sanitation? We've all heard about foodborne illnesses from everything from lettuce to meats and dairy products, but with shellfish, they have a unique risk to consumers because bivalves such as clams, mussels, oysters, any of those with the two shells, they are filter feeders, which allows them to concentrate pollutants around them into their bodies. So when we eat that, we're actually getting exposed to a concentrated source of pollution rather than just lettuce that's been washed with polluted water. So really with bivalves, we want clean water because that'll give us clean bivalves. And I have a video here, hopefully I can make it work, to demonstrate. Let's see.
Here it is.
Oh. See if I can move it forward. All right, so this was put together by Washington State Department of Health, and they wanted to demonstrate filter feeding. Let's So they have 4 tanks that they'll show you. And in one, obviously, they have seawater only. The second one, they have 20 blue mussels, and then 40 in the third, and then nothing in the fourth. And they're going to add algae to each of the tanks. And then they're going to let these mussels sit and filter feed to demonstrate how effective they are at pulling this stuff out of the environment. So filter feeders draw in water from around them and filter anything out that can fit into their mouth. And then they concentrate it in their bellies, digest what they're able to eat, and eventually release the rest into the environment. And that includes anything from algae, which is what they generally like to eat, I believe. But that'll also include viruses, bacteria, chemicals, oil, anything that's around them. They'll bring in and concentrate in their bodies. And as you can see, in an hour, they're doing a really great job of clearing up that water. So they're very effective at concentrating these things into their bodies if they're feeding. And they've almost got it completely cleared up within an hour and 15 minutes. So because of that, DMR operates under the National Shellfish Sanitation Program. We're overseen by the FDA, and they've set up this program to give us minimum requirements necessary to regulate the shellfish harvest here, to make sure it's safe for people to eat and that hopefully nobody gets sick. It gives us ways to classify the growing areas for harvest, monitor the water quality, biotoxins including ASP, DSP, and PSP, or red tide as you often hear it. And it even goes into safe handling and trace back. If there is a sickness, we're able to trace back where these came from and pull off as much of the shellfish off of the shelves as we can to make sure fewer people get sick. Because we want the shellfish that's for sale to be safe for us to eat. One of our closures that we've put in is emergency closures, and these are the ones that usually make the news. They're the often big closures, like our flood event that we have here from last fall. This was in September. We close for high rainfall, which we call a flood event. Any rain event over 2 inches washes a lot of pollution from the land into the water and exposes the shellfish. So we close down the coast every time we get 2 inches or more of rain. And you can see Taunton Bay right up here. So this is a very large closure that we have. We also do biotoxin, oil spills, dead whales. When they wash up on shore, we close around them. Anything that can adversely affect human health, we'll close around. But the majority of my job is about classifying growing areas, and these are more long-term closures. So most of my area is inapproved, thankfully. We have relatively clean water in our area of Maine, and that means anyone with a license can harvest shellfish. There's no restrictions. The shellfish should be safe. We also have some areas that are conditionally approved, which means people can only harvest shellfish under certain conditions. A lot of mine are seasonal areas, so in the summer when we get a lot of tourists, a lot more wildlife movement, we have higher bacteria, so I close down these areas in the summer, and you can only harvest in the winter. They'll open up again in the winter. We do them for rainfall events. Some places have bigger issues with only 1 inch of rain instead of our normal 2-inch closure, so we close earlier. We have them around marinas. We have some around tide height. There's all kinds of events, but they need to be predictable and stuff we can react to. We also have restricted areas, which you can only harvest there with a special license, and there's only a couple places that do those type of harvests. Spinney Creek is one in southern Maine, and they come in and collect shellfish, bring it back to their plant, and let it filter feed in clean water at their plant, and then they have to do testing before they can sell these shellfish onto the market. And then conditionally restricted, again, they can only harvest under certain conditions. And then prohibited, there means there's no harvest allowed there, and that's usually because there's a source of pollution. All of our wastewater treatment plants, they discharge water into our bays. People have failing septic systems in their houses. We have oil spills. We'll close it down and make them prohibited for a period of time. And this is a legal notice example of Frenchman's Bay. This is one of my main areas. You can see Taunton Bay up here at the top. So we have a little spackling of closures in this area. And here's your closures in Taunton Bay specifically. We have a couple prohibited areas in the head of Hog Bay and then over in Egypt Bay, and those are from pollution sources in the streams there, or just the streams themselves that are very dirty, so we've closed those down. And then in Springer Creek and in Millbrook, we have conditional areas based on season. So in the summer, when everyone moves back into their houses, we see a large uptick in bacteria. So we close those areas down for the summer, and then they open back up in the winter when it cleans up again. So part of our program is water quality monitoring. We collect seawater samples along the whole coast of Maine. We have over 1,000 samples, 1,170 stations along the whole coast. So we sample a lot, and each of these stations is sampled 6 to 12 times a year to help maintain our standards. We also do stream sampling on top of that and pollution source sampling. So if we find a pipe that's discharging on the shore, we might take a sample there. We monitor a lot of the streams as well. We have many streams in Maine, so we can't monitor all of them, but these help us meet bacteriological standards that are set by the National Shellfish Sanitation Program. With the most recent 30 seawater samples at each station, we calculate a 90th percentile, we call a P90, and a geometric mean, or geomean. And this is a calculation that helps weed out some of the noise that bacterial samples give you. Bacteria doesn't add one at a time, it grows exponentially. So some days we'll get huge numbers and some days we'll get smaller numbers, so that helps us clear out some of that noise in our sampling and give us a more accurate reading instead of taking just the average of the samples. Let's see. But the cornerstone of our program is our shoreline sanitary survey. Every 12 years, we're required to go to every house within, or every property within 250 feet of the shore and look at any sources of pollution that are from that property. And that includes everything from residential, industrial, agricultural pollution sources, marinas. There's endless sources of pollution on our shores. So we have to go evaluate all of them, check to see if there's any new issues that are impacting the shores, and then implement closures if we find any. And we inevitably do. These are some of the more PG pictures we have. But we have people that make up their own outhouses right next to streams, and this isn't a problem until they decide to dump out their buckets, and where are they dumping them? But we have septic systems that are blown out. This one's, you can even see the corners of their field starting to stick out here. But this is a campground that their pump station started failing, and you can see when we look for these issues, it's kind of like if anyone is a gardener, you accidentally dump a bunch of fertilizer in one spot on your ground, you'll get a big dead spot with really lush gardens around it. You can see the really lush gardens around this pump station where it was getting soaked with nutrient-rich water from their toilets. So these are all things that we look for and try to fix. Here's a very failing system. We see pipes a lot, holding tanks that never get pumped. So all of these, even though it seems like it's nothing, it's in the middle of someone's yard, 100 feet away from the shore. If there's a rainfall event, that washes all of that into the shore, and you don't know what viruses or whatever else they've got in the waste in those areas. So we try to close around those whenever we find them. And then here's a look at Taunton Bay. All of the dots are our sampling stations, and this is a unique area that I have to manage because, as Lauren was saying, this constriction creates a lot of interesting patterns up in here, and we tend to see more issues in these constricted bays that don't have a lot of flow. It's wonderful for creating beautiful mud flats for the clams to live in, and it's probably great for clam recruitment, but it's also great for holding on to bacteria for long periods of time. So sometimes one failing septic system in a tight area like this that has a high residence time would be a much bigger issue than one in Union River Bay where it would wash out right away. So the green dots are all areas that have a 90th percentile. That's very low. It's 2 to 15. As we get into yellow and orange, we're starting to get a little more concerned about those areas starting to fail. And then we would implement closures once we hit a black dot. So Springer Creek up at the top is one of the black dots that I had to implement a closure in this spring. It started failing, so I put in a seasonal area. And then red dots, thankfully we don't deal with those very often in this part of Maine, but we do in the more populated areas in southern Maine. Those, the bacteria concentrations are so high that we can't even allow depuration harvest. They're just too dirty to depurate. But in Hog Bay, or in Taunton Bay actually, you guys have seen a lot of cleaning of a lot of our stations are starting to clean up a little more recently. And we're not absolutely sure why. We go through cycles of that. Sometimes it's related to droughts, like we've had droughts for the last few years, so we aren't getting that bacteria from the shores flushing into the waters. Sometimes it's because people have started fixing up septic systems, or maybe the brooks have had vegetation grow around them, so they don't allow as much bacteria to wash in.
So is this the current one?
Yes, this is current to today. Yep.
Any impact by the oyster farm in that area?
On
the water, by cleaning the water more, you have more oysters?
Yeah, I mean that is a possibility. The more shellfish you have, the more it would filter that stuff out. But there is a lot of water. I don't think the oysters would make a lot of difference unless we were sampling right in there. But I know other states have done sampling right on oyster, like off of oyster rafts, and it depends on how much bird activity there is on there. Sometimes if there's a lot of bird activity, it can actually increase bacteria in that area. Depends on the time of year, what the birds are eating as well, so that can be kind of a mixed bag. But yeah, generally, I mean, they're filter feeders, so they will clean the water.
How often are all these sites tested?
6 times a year to 12 times a year. So our conditional areas in the blue, those are tested 12 times a year because we have to test 6 times a year when they're open. So we do it more often there. But 6 is our baseline. So all of our 90th percentiles are calculated with about a 5-year period of data because we use the most recent 30 samples.
So how far back does your data go as to these specific sites?
It depends on the area. Some of them are newer, like these are a couple sites that are newer. Those have only been around for about 10 years. But some of our sites go back to the early 90s. Yeah.
So I'm a homeowner. I live on the southern side of Taunton Bay.
Yep.
Right now I'm green.
Okay.
But at low tide, if I want to go out and do some clamming,
Mhm.
how do I know it's safe? I mean, is there something on your website that I could refer to?
Yeah, I can pull that up if you'd like.
Sure.
All right. So if you search Maine DMR Shellfish Sanitation,
Okay.
the first option that comes up is all of our legal notices. So these are the maps that I was showing, and you can look at the whole state. So then if you click back to our main page, we have, make sure I'm clicking on the right one. Yep, so we have a map there that you can go to, and this is an interactive GIS map. And we have our disclaimer so we don't get sued. So this is the map of the whole state, and we'll zoom right in on Taunton Bay. And on this map, we have lots of options for what you want to look at. And I think this is the map that was used to make the one in this booklet that you have.
Nice job.
So what I would suggest is going down to shellfish closures, and you want to look at emergency closures, municipal, biotoxin, and bacterial. You want to make sure all of them are clicked off. And then, let's see. Oh, sorry. And then we'll add the 2021 P90 scores. And you said you were on the bottom edge?
Yeah, right. Right,
Yeah. Is this one you?
yeah, just to the right of that.
Yeah. So to the right of that, you're not in any conservation closures, so you would be open and able to harvest right now.
Cool.
But if you click on each one of these, it'll pull up more information. This closure, let's see, was put in April. Yeah, and so you're not allowed to harvest here all year round.
Is that 'cause the clams are too young, or you want to keep the old ones? Or?
No, that one's one of the conservation closures put in by the Shellfish Committee, and that's because it used to mirror one of our actual closures that we had there. It was too dirty to harvest shellfish there, so they put in a conservation closure along with ours. Yeah, so one way you can tell the difference between clammers and wormers is clammers are more spotty. They'll dig one hole and walk a little bit and dig another hole. Wormers, you'll tend to see them digging row after rows. Those are usually wormers.
Okay.
Yep.
So the last 2 years, it's been wormers.
And Taunton Bay has a lot of worming activity. I don't think you have a very robust shellfish population throughout much of the bay.
No.
I know I heard especially at the top of the bay in Hog Bay, there's very few clams up there. It's mostly worms.
Is there something that we could do that would be useful for you?
Like looking at bacteria.
Yeah, bacteria-wise.
I mean, any data is helpful for us. We like information around rainfall events. That's usually seems to be one of the big drivers of bacteria into our bays. But we just don't have, we have to follow the FDA's guidance, so we don't have much wiggle room with the state to do anything beyond what we're actually assigned to do. But rainfall information is very helpful for us. Springer Creek and Millbrook are both areas that we have fluctuating bacterial issues with, and we have yet to find a source. We've done surveys there many times and not found any houses that are failing. But then again, those are hard to try with MST sometimes because of the limitations of that testing. It really looks only for mammals, human, birds, gulls. And so if you find that it's mammals, what do you do about the deer? You know, what do you do about the beavers that are causing those issues? So if we can find human sources, that's great. That would be helpful for us. And that's where I caution groups when they want to do that is they want to come out and fix the problem. And sometimes you're going to find out that the problem is not fixable. You can't go kill all the deer in the area or chase off all the seagulls to help protect it. You know, there's only so much you can do sometimes. But if you find a human source, it's a lot. It gives us something behind our enforcement actions then. Yeah, and that's one thing that people don't think about is pets in your yard. If you have a dog that you don't clean up after, all of that gets washed into the water, and we've had that alone shut down areas. And once we get, it's usually in parks, once we get the parks to start cleaning up animal waste, we are able to reopen areas. Yeah, that's one of the areas I'm looking at with my work with Sean. I'm looking at bacteria that ends up in the sediment and ends up growing in the sediment. So instead of having an actual source of pollution that's washing in, it's bacteria growing in the sediment, and then when we get windy days or large waves and it resuspends the sediment in the water column, that's where DMR is getting our high scores and not from an actual pollution source.
Lots of good information.
Thank you.
Yeah.